The record is start.
Okay, today our speaker is Yasemin Kara from Boğaziçi University. She obtained her PhD under supervision of Professor John Hubbard from Cornell University and was also a visiting student in France during her undergraduate work. Currently, she's an assistant professor at Boğaziçi University, and her research interests include geometry and spectra of hyperbolic manifolds, Laplacian on hyperbolic manifolds, automorphic forms, number theory, and arithmetic geometry. Let's welcome Yasemin Kara for today's talk.
Okay, thank you very much, Sami, for the nice introduction. First of all, I would like to thank everybody for the invitation. And it's a great honor for me to give a talk in this joint number theory seminar. Actually, I was supposed to give this talk in March in the first number theory joint meeting between Fezai Gürsey Center and IPM, but because of some personal issues, we had to cancel the talk. So I apologize for this. So let me start my talk. Today, I will talk about solving Fermat type equations by modular approach. One of the main problems in number theory is actually finding solution of Diophantine equations. So let's start by defining Diophantine equations. So a Diophantine equation is an indeterminate polynomial equation with integral coefficients for which we would like to find integral solutions. And here are some examples. The first one is just a linear equation. And the second one is an elliptic curve. And the third one is the famous Fermat equation. And the fourth one is the generalized Fermat equation. So you put coefficients in front of x to the n, y to the n, and z to the n. And of course, the powers do not have to be the same. So if the powers vary as PQR, we call it Fermat's equation with signature PQR. By the way, when you have questions, please stop me. Or if I go fast, you can also stop me. So let's start with the Fermat equation. And as everybody knows very well, so the Fermat's last theorem states that the equation x to the n plus y to the n plus z to the n is equal to 0 has no non-trivial integer solutions for n bigger than 2. Trivial means x, y, z is equal to 0. So actually, if you look at this equation a little bit, you will see that it is sufficient to consider cases n is equal to 4 and n is an odd prime. So if you can prove for these cases, actually you can prove Fermat's last theorem for any n bigger than 2. And n is equal to 4 was proven by Fermat himself. And for other smaller primes like 3, 5, and 7, many important mathematicians gave proofs like Eilar, Legendre, Dirichlet, Gauss, and Lamé. And for P is a regular prime, Schumer proved the statement. And a regular prime means P doesn't divide the class number of Q adjoint the P root of unity. And finally, in 1995, Wiles and Taylor proved the statement for any P, for any prime bigger than or equal to 3. So they proved that the Fermat equation has no non-trivial integer solutions. Of course, between Schumer and Wiles, there are many developments, but I didn't write all of them. And also, if you go back to late 19th century and the early 20th century, you can see some results about Fermat equation where mathematicians considered it over other number fields, not just for over rationals. And I will talk about this later. So first of all, let me concentrate on the Fermat equation over rationals. Okay. Okay, I think Semih has a question.
Just a remark for n equals 4 case, do we assume the equation is of the form x to the n plus y to the n minus z to the n is equal to 0? Or do we make sign changes with the terms, or it's again plus?
I don't remember now, but I mean, does it matter for the solution?
Well, if we're looking at
Yeah.
integers, yeah. Okay.
Okay. Is that okay, Semih, or?
Yeah, I mean, it was just a remark or.
Remark. Okay, thank you. And now, okay, so Weiss and Taylor proved this statement for primes in 1995, and the approach that they used is called modular approach. Now, let me talk about this approach a little bit. And so what they do is they assume that actually there is a solution for the equation. And then for this solution, they attach an elliptic curve to this solution. And then, of course, by using many important theorems, they show that this elliptic curve, which is actually called Frey elliptic curve, has properties conflicting to each other. Okay, and of course, while doing this, there are many important theorems that they use. And in the modular approach, we have three main ingredients. And one is the modularity theorem, which is proved by Wiles and Taylor-Wiles. And the other one is irreducibility of Galois representations. I will talk about them in more detail, which was proved by Mazur, and then level lowering theorem by Ribet. And okay, actually this proof brings different fields of mathematics together, which might seem, first of all, unrelated. And we have some objects which are very important for the proof. And one of them is elliptic curves. The other one is modular forms, and the other one is Galois representations. Okay. And actually, to compare elliptic curves and modular forms, you have to kind of the medium step is like Galois representations. So I will talk about each of them a little bit, and then talk about these main theorems. So what is an elliptic curve? An elliptic curve E over a field K is a smooth projective algebraic curve of genus 1, on which there is a specified point, and this point is called the point at infinity. And if the characteristic of your field is not 2 or 3, then your elliptic curve in non-homogeneous coordinates is given by y squared is equal to x cubed plus ax plus b, where of course a and b are in K. And actually, if you consider your the points on this elliptic curve with this point at infinity, and this gives, you can define you can define an operation on the points of this elliptic curve so that this E of K becomes a group. Okay, and by the way, smooth means there are no cusps or self-intersections. And here the picture is the picture of y squared is equal to x cubed minus 4x plus 6 over reals. Okay, any questions so far? Okay. So given an elliptic curve, we can reduce it modulo P. And we say that E has good reduction at P if the reduced curve, which I denoted by E tilde, is smooth. And we say that E has bad reduction at P if the reduced curve is singular. And there can be only finitely many bad primes. And the conductor of the elliptic curve, which is an invariant of the curve, encodes these bad primes. Okay, and I will, actually I didn't give the definition of the conductor, but I will use it over and over again. It's an invariant of the elliptic curve and it encodes the bad primes. Okay. Now consider this elliptic curve y squared is equal to x cubed minus x plus 1. And let's find the solutions modulo 3. So if you find the solutions modulo 3, then E of F3 with the point at infinity actually has 7 elements. And you can do this for all primes. Okay, so this NP denote the number of solutions mod P. And for this example, I made the table for small primes. And as you might guess, number of solution increases as P increases. Okay, and there is a reason why I am defining these things. For an elliptic curve E, we define AP as P plus 1 minus NP. And this AP will be important for us. Please try to remember the definition. And again, for this example, you see in the table P, NP, and AP. Okay, and this is all about what I will say about elliptic curves. And now let me talk about a little bit modular forms. Actually, I can give the general definition of an automorphic form, but I don't want to do that. So a modular form of weight 2k, and in this definition, I am only defining it with respect to SL2Z. So these are 2 by 2 matrices with integer entries and determinant 1. So a modular form of weight 2k is a holomorphic function on the upper half plane, which satisfies the written transformation property. So when you compose F with the Möbius transformation, it gives you f of c times cz plus d to the 2k. Sometimes this is called a modular form of weight k, but I use weight 2k. And of course, this modular form must satisfy some growth condition, which I didn't write. Okay, and I will repeat in this talk new form of level n all the time. So that means a special kind of modular form for the group gamma 0 n. So gamma 0 n is the upper triangular matrices modulo n. That means the lower left entry is 0 modulo n. Okay, and modular forms have power series representations since they are holomorphic. So you can write them as Cn q to the n, where q is e to the 2 pi I. So this is called the q expansion. Okay. Now let me introduce what we mean by Galois representations. So consider an elliptic curve over a field K, and M is an integer which is bigger than or equal to 1. So by EM, we denote the M torsion subgroup of E. That means it is the set of points of E of order M. Okay, so remember this E of K has a actually group structure, and that means if you apply this operation M times, you get the identity element. And also it is known that if the characteristic of K bar is 0, then actually this M torsion subgroup is isomorphic to Z over MZ squared. And now by G of K, we denote the absolute Galois group of K. And this absolute Galois group actually has an action on the p torsions of p torsion subgroup of E. So you obtain a representation from this absolute Galois group to automorphisms of these p torsion sub p torsion points. And this automorphism group is isomorphically clearly GL2FP. And this denotes, this rho EP, we say that it is the mod P Galois representation of the elliptic curve E.
So do you assume that characteristic is different from P?
In this case, you mean? Yeah, I assume that the characteristic of K bar is 0.
Thank you.
When you mean when we define the mod P Galois representation?
Yes, yes. You're saying that, do you assume that K has characteristic 0 or different from P? Is that the case?
In general, no.
For the mod P Galois representation of E. This definition.
The
P torsions are not necessarily FP squared, right? If the characteristic is P.
Yes, that's true.
So do you assume that's different from P?
Yes. I assume that's different than P. Okay. So now let me talk about these 3 main ingredients that I gave in the first slides: Modularity Theorem, Mazur's Theorem, and Ribet's Theorem. I will state them, of course, with not every detail, but I will try to explain what they mean. So the modularity theorem says that every elliptic curve over rationals is associated to a rational new form of level n. That means, in other words, there is a new form which we can represent by a series such that the coefficients of this new form, remember the definition of this AL, that was by definition L plus 1 minus the cardinality of the number of points of the elliptic curve over FL. But here L is a prime. CL is equal to ALE for almost for all primes except finitely many. I didn't write the details, but they are not equal for all primes. They are equal for almost all primes. And this is what modularity theorem says without giving the details. And the Mazur's theorem, so it says that if you have an elliptic curve over rationals with full 2 torsion, then E doesn't have any P isogenies for P bigger than or equal to 5. Actually, this means the Galois representations attached to the elliptic curve for each P are irreducible. So irreducible means, in this case, they are not upper triangular. And Ribet's theorem says that, you can, for your elliptic curve E, you can attach some new form, but sometimes it is possible to replace F by another new form of smaller level. If you have the modularity of E and the irreducibility of mod P Galois representations. And so this is the Ribet's theorem. So you can lower the level. So actually this is called level lowering theorem. Okay. Now I will give very basic sketch of the Fermat's last theorem. So you assume that ABC is a solution and you can scale ABC so that they become co-prime integers, and you can even put more conditions. And then you attach the Frey elliptic curve to this solution, and it is y squared is equal to x minus a to the p, x plus b to the p. And then this rho EP denotes its mod P Galois representation. And then for each P, actually these mod P Galois representations are irreducible by Mazur's work. And Weiss proved that actually elliptic, semi-stable elliptic curves are modular over rationals. And so then you apply, so that means there is a new form which you, that you can attach to your Frey curve. Then you apply the Ribet's level lowering theorem and conclude that actually these representations arises from a weight 2 new form f of level 2. And the point here is that actually you can calculate the dimensions of the spaces of these new forms. So actually you know whether or not you have any new form of a particular weight at a particular level. And from the computations, actually you see that there are no such new forms at this level. So you get a contradiction. Since you get a contradiction, that means actually the Fermat equation does not have any solutions. So this is really a very basic sketch of the Fermat's last theorem over rationals. Any questions so far? Okay. Now, what is RA? By the way, at the beginning, I talked about the history of the Fermat's last theorem a little bit. But I told you that mathematicians, even like in the late 19th century and the beginning of the 20th century, try to solve this Fermat's equation over some other number fields. And I think, for example, first of all, they tried to apply Kummer's method for cyclotomic fields. And then later, I think in the 1980s, there were some results about quadratic fields, okay? And so the aim is actually to consider this Fermat equation over higher degree number fields. So instead of Q, we take a number field K. Instead of integers, we consider the ring of integers of this number field K. And P is a prime. So we refer the equation, the same equation actually, A to the P plus B to the P plus C to the P is equal to 0, as the Fermat equation over K with the exponent P. Of course, here now ABC are elements of the ring of integers of K. And now there is a conjecture which is called asymptotic Fermat conjecture. And it says that if you take a number field K, such that the third root of unity is not a member of K, then there is a constant which depends on known K, such that for any prime bigger than this constant, all solutions are trivial. Okay, now you can ask two questions. Why do we require that the third root of unity is not in K? Because if it is in K and if P is not 3, then you can see that 1 to the P plus this zeta 3 to the P plus zeta 3 to 2P satisfies the equation. So we have to exclude number fields such that the third root of unity is an element of K. And you can ask again, why it says for a prime bigger than a constant which depends on k. It doesn't say for all primes. The reason is that because for smaller primes, actually you can, and on some number fields, you can find the solutions. Okay, so there are solutions. So this is why we have asymptotic Fermat conjecture. So that's the statement. Any questions about the statement? Okay. Now here, let me say some of the works towards this conjecture. These are some earlier works. And one method was you treat the Fermat equation with fixed exponent p as a curve and determine the points of low degree. And low degree, that means points defined over number fields of low degree on your curve. And for example, by using this method, Gross and Rohlwig determined the solutions of the Fermat equation over number fields k, whose degrees are less than or equal to p minus 1 over 2 for p, 3, 5, 7, and 11. Okay, but another method is, the question is actually, can we use this modular approach to get results on the asymptotic Fermat conjecture? And towards this direction, the first result is due to Jarvis and Mekin in 2004. They proved that the Fermat equation has no solutions in the quadratic field q square root of 2. I mean, no non-trivial solutions, and n is bigger than or equal to 4. And as you see here, they just prove it for just one number field. So they show that for this particular number field, the Fermat equation has no solutions. Okay, but our aim is actually to get a result for many number fields, and not as in the first approach. In the first approach, they fix P. We don't want to fix P. We don't want to fix any number field. So we would like to vary number fields, and we would like to vary P. Okay, and actually, we will see some results where the modular approach is applied to asymptotic Fermat conjecture. But before starting to state the results, I would like to give the motivation. Okay, so we look at an example which is given by Sars and Maser. So Sars did this example in his paper where he formulated his famous Sars modularity conjecture. So he considered the equation x to the p plus y to the p plus l to the r z to the p is equal to 0. Here, L is either 1 or an odd prime. P is bigger than or equal to 5 and prime. P is not equal to L. And actually, you can assume that R is bigger than P, but I mean, it doesn't matter, because then you can absorb p powers of L into z to the p. So you can assume that R is actually between 0 and p. And here you see that if L is 1, actually this is the Fermat equation. So they considered this example, and they assume that there is actually a non-trivial solution where x, y, and LZ, they do not have any common divisor. Okay, let's call, instead of writing x to the p, y to the p, l to the r, z to the p each time, let's give them names, and let's call them capital A, B, C. And you can actually assume that A is congruent to -1 mod 4 and 2 divides P. This is actually also done in the proof of Fermat's last theorem over Q, the same trick. And then you attach this Frey curve. Okay. And now, when you again apply Mazur's theorem, Weiss and Ribet's theorem, what you get is you can attach any form of weight 2, and this time level is equal to 2L. Okay. And this is what you get. Remember, in the Fermat's last theorem case, since L is 1, what you get is you attach your elliptic curve any form of weight 2 and level 2. This time it is 2L. So the L1 case is Fermat's last theorem case. And there we concluded that there are no forms of weight 2 and level 2. So that means there are actually no non-trivial solutions. But unfortunately, this time, there are new forms of weight 2. Okay, for the levels 6, 10, and 22, there are again no new forms of weight 2. So again, in these cases, that means there are no non-trivial solutions. But how about the other primes? Now we have again infinitely many primes. In these cases, there are new forms of weight 2. Okay, then what did they do? So in this case, you need to study the relationship between E and your F. And remember, this F has an Q expansion. Okay, by the way, in this example, there are many details about the calculations. I will not give all of them. I am trying to give the motivation and idea behind this example. Okay, so what you do is you study the relationship between your curve and this F. Okay, now define any field which you denote by Kf by adjoining these coefficients of your modular form to Q. Okay. And actually, in this case, you can prove that this Kf is totally real. And this actually Cns belongs to the ring of integers of Kf. Okay, and here there's a definition. Any form F is called irrational if this Kf is not equal to Q. It's called rational if this Kf is equal to Q. Okay, and then it can be shown that if F is irrational, actually then you can bound the exponent for non-trivial solutions. For example, for L is equal to 37. This means that then you can exclude this case, okay? So if F is irrational, you don't, because you find a bound for the exponent P, then now it doesn't matter. But again, for all other L's, these F's are rational for the remaining cases. Okay, so you still don't get a contradiction. Okay, then there is a Eilar-Schumer relation, which is true in this case, a theorem. It says that a rational weight 2 level any form F corresponds to an isogenic class of elliptic curves E prime defined over Q of conductor N. Okay, so now instead of working with your original E, you can work with E prime. Okay, and in this case again, you can do lots of calculations, and there are cases again where you can bound the exponent P, so that means they are not a problem for you anymore. Then you can read but still there are there are primes which cause problems, but you can reduce to the case in which E prime is isogenous to an elliptic curve with full 2 torsion. Again, by using some theorems. So here, in each case, you get rid of from some cases. And finally, you have a case where you have E prime, which is isogenous to an elliptic curve with full 2 torsion. And such E primes and such odd primes L, for which there is an elliptic curve E prime over Q with full 2 torsion and conductor 2L, these are the problematic cases. Now the question becomes, what are the odd primes L for which there is an elliptic curve E prime over rationals with full 2 torsion and conductor 2L? Okay. And then they prove a lemma, let L be an odd prime. Then there is an elliptic curve E prime over Q with full 2 torsion and conductor 2L if and only if L is a Mersenne or a Fermat prime and L is bigger than or equal to 31. Okay, so after this lemma, actually what they proved is the following. Let L be an odd prime. Suppose L is less than 31 or L is neither a Mersenne nor a Fermat prime. Then in this case, you can find a constant such that for all primes bigger than this constant, you have only trivial solutions to the equation x to the p plus y to the p plus r to the r z to the p is equal to 0. Okay, so as you see, the moral of this example is that you are not able to get a contradiction immediately. Okay, step by step you have to eliminate cases, and in this lemma actually I wrote the proof. The reason is because we have an equation which is called S-unit equation, which will be important for us. So since E prime has full 2 torsion and conductor 2L, it has necessarily a model of this form, y squared is equal to x times x minus a, x plus b, with the conditions ab times a plus b is not 0, and the discriminant is given by this number there. And actually you can choose a and b so that the model becomes minimal away from 2. Okay, so that means then a squared b squared times a plus b squared is equal to 2 to the u times L to the v for some negative integers u and v. And you can actually solve a and b in terms of, A and B have some spatial pattern, some spatial format, like 2 to the U1, L to the V1, such that A plus B is also of the form plus or minus 2 times U to the 3, L times V to the 3. So the moral of this example is that actually everything is reduces to solving a kind of spatial type of unit equation. And in this case, this equation, 2 to the U1, L to the V1, plus or minus 2 to the U2, L to the V2 is equal to plus or minus 2 to the U3, L to the V3, is called an S-unit equation, where your S is 2n L. I will explain what an S-unit equation in a minute. So it is possible to relate non-trivial solutions of Fermat type equations to solutions of certain S-unit equations. Okay, because we are not able to get a contradiction immediately. So what we get at the end is we relate non-trivial solutions to the solutions of certain S-unit equations. Okay, now let me define actually what we mean by an S-unit equation and S-units. So if you have a number field K, then by O of k, we denote its ring of integers. Here, S is a finite set of prime ideals of this ring of integers, okay? So by S integers in K, we mean the elements of K star such that the valuation of alpha at B is non-negative for all primes which are not in S. And S unit means that the valuation of alpha is 0 for all primes that are not in S. Actually, that means, so alpha is an S unit if the principal fractional ideal generated by alpha can be written as a product of the prime ideals in S. So the S unit equation is done by definition. Lambda plus mu is 1, where lambda and mu are S units. Okay, any questions, by the way, so far? Okay, so let me give some examples. For example, if our field is rational numbers, then of course ring of integers is just integers. And let's say that in S we have just 2. Then in this case, you can actually see that the S integers are of the form plus or minus 2 to the Rm, where m and r are integers, and S units are just of the form plus or minus 2 to the R. And the S unit equation, if you solve it, you have just actually 3 solutions, 3 pairs. If you're in the next example, this is the example actually where Sar and Maser considered. If K is rationals, if your S is 2 and L, and the S integers and the S units are of this form. And we can give more examples. So here we have a quadratic real field. And in this case, if you take S empty set, then the S units are of the form 1 plus or minus 1 plus square root of 5 over 2 to the R. And you have just one S unit solution. By the way, actually, there is an algorithm which gives you the S units. So if you have an S unit equation, you can compute the S units, and there are only finitely many of them. Okay, so this was a remark. So now let's go back our asymptotic Fermat conjecture. So the conjecture says that, let me remind you again. So if you have a number field which doesn't contain the third root of unity, then there is a constant which depends only on your field, such that for any prime bigger than this constant, you have only trivial solutions. Okay, and one of the first satisfactory answer to asymptotic Fermat conjecture was given by Feritas and Siksek in 2015. So they actually, if you take a totally real field, they showed that the asymptotic Fermat conjecture holds for K, satisfying some explicitly given algorithmically testable criterion. And you can guess that this actually criterion is given in terms of some solutions of S units. Hopefully, it is clear from our previous example. So, for example, in particular, they show that their criterion is satisfied satisfied by a subset of real quadratic fields, which has density 5 over 6. Okay, and this density becomes 1 if they assume Eilar Schumer conjecture. Okay, and here, if you don't want to prove that the density is 1, so that means you don't have to assume the conjecture. Actually, in the real, totally real field case, you have the modularity theorem. You have the level lowering theorem, and actually, I mean, they proved it in some of their previous papers. And you have also irreducibility of mod P Galois representations. You just enough of all these big theorems to prove that for totally real fields, actually this asymptotic Fermat conjecture is true. And later, Schengen and Zixek considered this asymptotic Fermat conjecture over any number field. But this time, when you take any number field, unfortunately, you don't have the modularity theorem, okay? They have it if K is totally real field, but for an arbitrary number field, they don't have the modularity theorem. This is the theorem that was proved for rationals, okay? So it's the big, big theorem. So they have it only for totally real fields. But in this case, if you assume the modularity, then you can actually prove the asymptotic Fermat conjecture for any number field. But here you have to assume this modularity result. So this modularity is in quotation. So let me explain these assumptions a little bit more. Okay. So this is the, by the way, if you have a totally real number field, this is the Eilar Schumer conjecture. So it says that for total number, you have a total number, total real field, and F is an Hilbert-Neff form of level n, which is parallel weight 2. You don't have to know these definitions. With rational eigenvalues, then you can find an elliptic curve with conductor n having the same L function as this F. This is the Eilar-Schumer conjecture. Okay, but so if you would like to prove this asymptotic Fermat conjecture for arbitrary number fields, then here actually, when we say modularity assumption, actually you have two assumptions. One of them is a version of Eilar-Schumer for an arbitrary number field. Eilar-Schumer for an arbitrary number field, it is different than if K is totally real field. Here, this conjecture associates to a weight 2 cusp form with rational Hecke eigenvalues, either an elliptic curve or a fake elliptic curve. I will explain what fake elliptic curve means later. So, but in the previous result, in the previous conjecture, if K is a total number field, then between Hilbert-Neff forms of level n, the corresponding curve is just a genuine elliptic curve. But if K is just an arbitrary number field, you can have either an elliptic curve or fake elliptic curve. And also here they assume what is called Sars weak modularity conjecture. So this conjecture, again, I didn't write all the details. So it associates a totally odd continuous finite flat absolutely irreducible two-dimensional mod P representation of absolute Galois group of K, a cusp form of parallel weight 2 whose level is equal to 2 prime to P part of the Artin conductor of the representation. This is too technical, but this 1 and 2 together is called modularity, because for a general number field, we don't have the modularity theorem. Okay. So in this case, so if you assume these assumptions, these conjectures, they prove that asymptotic Fermat theorem holds for any number field. So you have these three big ingredients, these three big theorems. You have two of them, but you don't have the modularity, so you have to assume the conjectures. Okay, so now let me talk about our results. So we take an arbitrary number field, and O of k denotes its ring of integers, and p is a prime. Now we look at a generalized Fermat equation. So that means you have coefficients a, b, c in the front of x to the p, y to the p, and z to the p. Here a, b, c are from ring of integers of k, and they are odd. Okay, what does it mean, an odd integer in this case? Okay, if 2 divides an integer, if 2 doesn't divide an integer n, then it's odd. In this case, what you do is, if you take a prime of, if you take a prime lying over 2, if this prime doesn't divide ABC, then ABC are called odd integers. So again, since we do not have the modularity for a general number field, we assume the conjecture. Okay, and then what we get with Ekin-Özman is the following theorem. You take a number field satisfying the modularity, and you have the set of S units. Here, your S is set of primes dividing 2 ABC. You have your S unit equation, and then you suppose that for every solution of this S unit equation, if you can find a prime in U, here this U is a subset of S, which has some nice properties, which I didn't write here. And if these S unit solutions satisfy a valuation condition, which is given by an inequality, so the maximum of the absolute value of the valuation of lambda and mu at beta is less than or equal to 4 times the valuation of 2 at beta. Okay, if your field satisfies such an inequality, then you can prove that there is a constant beta depending on your field, of course, then A, B, and C. Then you can prove that for any exponent bigger than this constant, the Fermat equation, the general Fermat equation, doesn't have any non-trivial solution. Okay, now you can ask, here there is a criterion which needs to be satisfied. Can you provide any number field actually which satisfies this criterion? Okay, that's the question. And then we prove that again, just a minute, Semih. If you assume the modularity, then actually this asymptotic Fermat conjecture is true for a subset of imaginary quadratic number fields, which has density 5/6. So we have actually lots of fields which satisfy this criterion. And so this was the density theorem. And then another theorem is just again about quadratic imaginary fields, which satisfies some properties written there. And of course, you need to assume modularity each time. Then in this case, you can prove that again, you can find a constant depending K and Q, such that for all primes bigger than this constant, X to the P, Y to the P, Q to the R, Z to the P, doesn't have any non-trivial solutions. Okay, I can take your question, Semih.
In the previous slide, what was U?
U was a subset of S. S is the set of primes dividing 2ABC, but it satisfies some conditions. But I didn't write the conditions. U was a subset of S. So in this S, you have only finitely many primes. U is a subset of it. which satisfies some properties. So the elements in U satisfy some properties.
Okay.
Okay. And another theorem is, again, if you take imaginary quadratic fields with these conditions, then again, the asymptotic Fermat conjecture holds for x to the p plus y to the p plus z to the p is equal to 0. Okay, any questions so far? So we find a criterion which depends on these solutions of the S units. And if your field satisfies this criterion, and of course you assume modularity, then the asymptotic Fermat conjecture holds. And as I said, we found actually infinitely many imaginary quadratic number fields which satisfies the criterion with density 5/6. Okay, now let me compare the two density results. Remember, Feritas and Siksek, they had also a density result. If for totally real fields, they also have a subset of real quadratic number fields which satisfy the where the asymptotic Fermat conjecture holds, and this set has density 5/6. But if they assume Eilar Schumer, then the density becomes 1. We already assume Eilar Schumer, but our density is just 5/6. And you might ask why there is a difference. Okay, and now let me explain this. So in Feritas and Siksek, when they assume Eilar and Schumer, the asymptotic Fermat conjecture holds for a set of real quadratic fields of density 1. In our case, when we assume the same conjecture even a little bit more, the asymptotic Fermat conjecture holds only for a set of imaginary quadratic number fields where the density is 5/6. Okay, the reason is because the conclusion of the Eilar-Schumer conjecture over real quadratic fields is stronger than the conclusions of the Eilar-Schumer over imaginary quadratic fields. Okay, what do I mean? I mean the following. For real quadratic fields, remember, a rational weight 2 Hilbert eigenform, f/k, corresponds to an genuine elliptic curve. But if k is imaginary quadratic field, remember, then you have some eigenform. In this case, it's called Bianchi eigenform. The name doesn't matter so much. It corresponds to either an elliptic curve or a fake elliptic curve. A fake elliptic curve, A/k, means actually an abelian surface whose endomorphism algebra is an indefinite division quaternion algebra. So what happens for the imaginary quadratic number fields? You can show that if 2 splits or ramifies in K, then actually you can eliminate the fake elliptic curves. But if 2 is inert in your imaginary quadratic field, that means if and only if minus d is equivalent to 5 mod 8, then unfortunately you cannot eliminate these fake elliptic curves. Okay, and these inert, so these the number fields where 2 is inert exactly corresponds to the 1/6 of the all imaginary quadratic fields. So the reason is the difference between Eilar-Schumer conjecture over total real fields or just for any arbitrary number field. Okay, so there is why there is a difference in the density theorems even though we assume the Eilar Schumer. Any questions? Okay. So what is the idea behind the proof here again? You attach the Frey curve, and if you have a totally real field, as I said, you have the modularity, irreducibility, and level lowering. But if you take a general number field, of course, you don't have the modularity, so you assume it. Then the steps are very similar to the steps of Fermat's last theorem over Q. Then after you apply these big theorems, you get a new form of weight 2 and some level n. But here, as in the example of Serre and Maser, unfortunately, there are new forms at the level n. So you cannot get the contradiction immediately. So what you do is, for P sufficiently large, instead of E, you can work with E prime with full 2 torsion and good reduction outside the prime factors of n. And then you can parameterize such E prime with the solution of the S unit equation. And then because you have some conditions on the valuation of these S units, then you get a contradiction. Here actually the details of the proof. I don't know, maybe just let me talk about a little bit about signature PP2, and if you would like to ask questions about the proof, I can explain. So also again with Ekin Özman and Erman Işık, we also considered the Fermat equation with the signature PP2. That means we look at the equation x to the p plus y to the p is equal to z squared. And actually, Watsal, Bennett, Yazdani, and Bennett Skinner has some results of this type of equations with the signature PP2 and PP3 over rationals. Okay, but instead of rationals, we wanted to look at any number field, and we would like to see whether or not we can use the same strategy here. Okay, here of course the powers are not symmetric, so as a result of this, the Frey curve that you get is not as nice as the Frey curve that you get for the Fermat equation. Okay, for the Fermat equation you get a nice Frey curve. Y square is equal to x times x minus the first curve. But for x to the p plus y to the p and z squared, you have y squared is equal to x cubed plus 4c x squared plus 4a to the p x. Okay, so we have a result, but in this case, just solving the S unit equation over k was not enough. So we need to solve a similar S unit equation over some extensions of k. So what we got is the following. Here again, we had to work with total real number fields with narrow class number 1. So here we look at the S unit, the solution of the S units on k, but also solutions of the S units over L, where L is defined as k adjoint square root of A, where A belongs to n Selmal group of K and Sk. But here you have this Selmal group is finite, so you only check finitely many extensions actually. So you have a similar criteria, actually the same criteria, but you need to check it over K and also over finitely many extensions of L. So if these criterion are satisfied, then again, you can find a constant depending on k. But in this case, we are able to prove for p bigger than this constant, the equation has no solution, but this solution has a spatial type. Okay, we were not able to prove that for all p bigger than this constant, we do not have any non-trivial solution, but we able to prove that there are no solutions which has a spatial type. Okay, and this here you can see the details of how these solutions look like. Okay, and also now we look at the equation where the signature is pp3. Okay, thank you very much. Do you have any questions? Because I think he just, I didn't explain the proof of the main theorem in detail, but I gave the idea behind the proof. Any questions? Any comments?
One question. Can you hear me?
Yes.
Okay, so what was WK in the last slide?
Okay, WK. So these WKs are a set of spatial solutions. I mean, these solutions have a spatial form. So these are the solutions of the form ABC, such that this beta, where this T is again a subset of this S. Remember, we defined a set S. This T was a subset of this S, such that the primes in this set divides B. So we were able to prove that we do not have solutions of this type, ABC, where this beta divides B.
I see.
Uh,
So that means that so probably you mean the curly P divides AB, because
no,
there's
it only divides.
there's not a symmetry between A and B, little a and little b. In the
I mean, there is no symmetry definitely. I mean, A and B doesn't matter in the proof. You can also take such that B divides A. But of course, there is no symmetry with like A and C and B and C.
Right.
Okay. So actually, I mean, without loss of generality, we say that let's beta divides B. You can also say beta divides A, but
Right.
not C.
I see. Okay. And so the difference between TK and SK is
okay, these actually, I mean, as I said, I didn't give the definition, but we have this set S. This set has,
I see. Okay.
yeah, this set has only finitely many primes on it. For example, in the generalized Fermat theorem case, they consist of primes which divides 2ABC. So you have finite of them, and this T, and it was U in the other theorem. So these are subsets of this S, but they satisfy some nice properties about valuations, but I didn't write them because then the theorem will be too long. But this TK is a subset of this S.
Okay, thank you.
Okay, any other questions or any comment?
Excuse me, I have one question.
Yes.
Is the asymptotic Fermat conjecture related to the Langlands conjecture?
I mean, the weak form of Sars modularity conjecture is, I think, a part of a part of the Lagrange program, might be. I mean, so the conjecture that we used, but maybe there are other relations that I don't know. Did I answer your question? I am not sure.
Thank you.
Okay. Okay. Other questions, or can I stop sharing? What is the plan?
Well, look,
Okay, any questions? So many thank you, Professor Kara, for your excellent talk, and for your time. So I should
Okay, thank
stop
you
the
very much.
recording.